Hello everyone, welcome to the Spin Journal Club presentation series. Today I am going to talk about reservoir computing with random Skyrmions textures. I would like to start with the definition of reservoir computing. Basically, what is reservoir computing? Reservoir computing is a neural network where a reservoir is between input and output channels. The input signal is sent to proper output channels according to the nonlinear response of the reservoir. It is based on how the brain works and the communication between synapses. For example, we can think of basic visualization process. When you look at an object, the input signal is generated by the photons reflected from the surface of the object, and the response created by the eye is recognized as object by the brain. In this paper, Skyrmion fabrics are used as reservoir, and the K concept is the nonlinear response of the reservoir. Signal theory states that if you know the output of direct delta function, which is a concentrated impulse at t equals 0, you can construct your outputs for any given input. Since you can write your input signals as linear, scaled, and shifted combinations of impulse function. However, this is only valid for linear case. On the other hand, the linear relationship between input and output is something that we don't want in reservoir computing, because we want to characterize input signals and classify them as zeros and ones, rather than the correct output characterization of the impulse function. In summary, reservoir computing aims to recognize patterns by the nonlinear dynamical response of the Skyrmions. And this feature enables applications such as signal prediction and memory functionality. Let's continue with the micromagnetic model used in this paper. As you can see from the figures, the geometry of the structure is a rectangle with lateral dimensions of 500 nanometer and 250 nanometer. The thickness is equal to 1 nanometer, and the structure is discretized into cubes with volume of 1 nanometer cube. You can see the Skyrmions used as reservoir in figure B, and the yellow circles are the contact points. And in figure C, you can see the corresponding current density distribution for an applied voltage of 110 millivolts. The material used in the structure is copy B, and these are the material parameters. Saturation magnetization is equal to 956 coulomb per meter. Exchange constant is equal to 10 picojoule per meter. And there is out-of-plane anisotropy, and the anisotropy constant is equal to 0.717 megajoule per meter cube. And there is also an external applied magnetic field with magnitude of 400 millitesla, and the Gilbert damping coefficient is equal to 0.2. Unlike many micromagnetic models, the IDMI is not uniform over the volume. This is achieved by the introduction of granular structure. The granular structure is introduced randomly with some specific mean value, and IDMI values from 0 to 8 millijoule per meter square are assigned to each grain. Skyrmions used as reservoir need to be tested in terms of their stability to check whether they are disturbed by thermal noise and current-mediated transport effects. For that reason, firstly, an array of Skyrmions is introduced artificially, and then they are relaxed under an externally applied magnetic field with magnitude of 400 millitesla. What I mean by artificially is that the vector field object that corresponds to the magnetization configuration is imported to the micromagnetic model by hand. And a thermal noise at 300 Kelvin is added to the structure for 20 nanoseconds and switched off. As you can see from figures C and D, there is no significant change between the states. And to check the volatility of the Skyrmions in the presence of spin torque, at 20 nanoseconds, constant voltage pulse is applied to verify that Skyrmions are indeed not displaced. And they concluded that Skyrmions are not disturbed by thermal noise and current-mediated transport effects. And this fact is attributed to the inhomogeneous IDMI, which is formed as a result of granular structure. The rest of the paper is about linear and non-linear anisotropic magnetoresistance of reservoir to input signals. So let's briefly talk about what is anisotropic magnetoresistance, shortly AMR. AMR is the resistance value that depends on the angle between magnetization vector and current density vector. If you keep the current density vector constant both in magnitude and in direction, the change in magnetization will create a change in resistance, and you can detect that resistance change. There are various ways for the manipulation of magnetization. For example, you can rotate your sample while keeping the externally applied magnetic fields, applied magnetic field constant in both magnitude and direction. Also, you can keep the sample and the direction of your externally applied magnetic field constant while sweeping the magnitude of the externally applied magnetic field. However, in this paper, the focus is on the manipulation of the magnetization with spin torque. Actually, what kind of spin torque is applied doesn't matter, because this paper is carried out only by means of simulation. So this is the equation of AMR. It is a well-defined equation, and according to this equation, we can suggest that maximum resistance occurs when current, density vector, and magnetization are parallel to each other, and also minimum resistance occurs when current, density vector, and magnetization are perpendicular to each other. One common problem with anisotropic resistance is that the signal amplitude can be very low and hard to detect. This problem can be improved with the insertion of insulator tunnel barrier between two ferromagnetic layers. This resistance is called tunneling magnetoresistance. However, tunneling a structure for tunneling magnetoresistance measurements is relatively harder to fabricate because there are vertical contacts, and the tunnel barrier, insulator tunnel barrier between ferromagnetic layers must be very smooth and very thin. So I want to show you a video of how spin torque affects the magnetization, in particular spin orbit torque. As I mentioned before, the kind of spin torque doesn't matter for the purposes of paper. You can modify your experimental structure for possible spin torque applications. For example, if you can deposit a heavy metal layer on top of your ferromagnetic layer, you can apply spin orbit torque. Also, if you construct a spin wave structure, you can apply spin transfer torque. This is the stripe domain structure that belongs to copy B at Z remnant state, and the black region is the contact point. As you can see, when the spin polarized current is injected to the ferromagnetic layer, it applies a torque on magnetization, and in this way, the magnetization is manipulated, and you can detect this change in the form of anisotropic magnetoresistance. So this is the part where the reservoir computing is actually performed. In the first experiment, 1 GHz sine and square pulses with 1 nanosecond between them are sent to the structure. And the reason for 1 nanosecond gap between the pulses is to observe the individual responses to the pulses. As you can see from the figure A, the resistance goes back to its initial value after approximately 0.6 nanoseconds. And these are the black rectangles are the individual responses. And those responses will be used for linear reconstruction in the second experiment. In the second experiment, a pulse train, which consists of, again, sine and square waves at 1 GHz in a random fashion, are sent to the structure, and we again look at the AMR response. As you can see from the figure B, the physical response, the red one, and the linear reconstruction, the yellow one, differ from each other. There are two important outcomes of this experiment. The first one, since the AMR response is nonlinear, we can use this system for reservoir computing. And the second important outcome is that the reservoir itself has a short time memory. It is history dependent, which means that the current AMR response not only dependent on the current driving voltage, but also it depends on the previous input signals, and this gives the possibility to recognize not only the current input signal, but also former input signals. As you can see from the figure C1 and C3, the nonlinear response, nonlinear AMR response of sine square pulse and square pulse are different from each other. Here, the same experiments are performed for 5 GHz. And as you can see from the figure E, the physical response and linear reconstruction agree well with each other. And the physical explanation behind is that AMR cannot fully interact with the applied voltage, and the reservoir itself has a short time memory. These two effects together produces an AMR response, a same AMR response for any given input signal. And so what determines whether the system is linear or nonlinear? The answer is ferromagnetic resonance frequency. Above ferromagnetic resonance frequency, such as 5 GHz, the signal is so fast that AMR do not have enough time to fully interact with the applied voltage. On the other hand, around with the ferromagnetic resonance frequency, AMR has sufficient time to interact with the applied voltage, and the system behaves non-linearly, and we can actually perform reservoir computing applications in that case. Here, I will talk about how the patterns are recognized and used for possible memory functionality implementation. As I mentioned before, the K concept in this paper is the nonlinearity, and the driving frequency is chosen such that where the nonlinearities are largest. Firstly, the nonlinear AMR response is trained for pattern recognition, and then the resistance sample values, the red dots, are measured at certain time points with regular time intervals. You can think of measuring the resistance values by a multimeter with time steps of 0.1 nanoseconds, and these values forms the resistance sample vector of the standard linear model for machine learning. And this vector is then multiplied by the weight matrix to give the best possible output vector, which consists of zeros and ones. The weight matrix is calculated by error minimization with a method called gradient descent. As a result, they successfully achieved that to recognize the input signals in 3 nanosecond range with a time resolution of 0.1 nanoseconds. In summary, we can say that pattern of the pulses are recognized by training up to 98% for present and latent pulses, which corresponds the time range from 0 to 2 nanoseconds, and 80% for past pulse, which corresponds to time range from 2 nanosecond to 3 nanosecond range with 10 resistance samples. In conclusion, they have achieved pinning of Skyrmions with the granular structure. They also observe linear and nonlinear regimes for reservoir response, and they have also successfully recognized the input signals in the 3 nanosecond range with 0.1 nanosecond time resolution. However, there are very drawbacks. For example, thermal effects are neglected in AMR response. The IDMI strength values are impractical, and also the accompanying Ørsted field is not included to micromagnetic model, and the operation is only possible under external applied magnetic field. Thank you for listening.